Good afternoon. My presentation is about edge processing, and it's motivated by the work in two projects two research projects that we have here. One is Brainy, and the other is Cluster 4.0. So the Brainy project is focused directly on data processing at the edge, and part of the project is development of a novel edge architecture, which will have less power consumption and less space demands and so on. This is not what we deal with, but our case is. And here you can see further features the architecture, the brain platform or the Brainy architecture is supposed to have. Our part is focused on validation of the platform on various use cases, and specifically the use case that we are responsible for is about robotics and Industry 4.0. This use case has two parts. One is focusing on robotics and production, and the other is focusing on data analysis and machine learning from the data. So I will start with this other part. Here you can see the data processing pipeline relating to this use case. It's based on the fact that we have some machines which provide sensory data, and these data are quite fast, and so the latency is below 100 milliseconds, but could be definitely faster. It's mainly limited by the communication protocol or the communication system that is used to get data from the robots, from the machines. And also the throughput is at around tens of kilobits per second. The core of the solution is this part where we, together with partner in this project, Factorial Solutions, developed a tool for discovering the patterns or searching for the patterns, and then learning of the behavior models based on the patterns. And what is important that this runs on the edge architecture, which can in fact be any edge, but with respect to the project is focused on the Brainy architecture based on the micro data centers. So there are two parts. One is about pattern discovery, and within this, problem solving, we developed a new algorithm focusing on searching of motifs. In fact, motifs are patterns which are repeated in the time series data with variable length. And the task was to develop the algorithm which is as efficient as possible. We managed to have linear time complexity up to tens of millions of samples, which is really good compared to other approaches where the quadratic complexity is mostly the case. And what is also interesting is the high success rate of finding the motifs and in fact covering most of the motifs that are present in the time series. Another part of this module is behavior learning and detection of behavior models that are in the data. For that, we improved or developed an extension to time-varying hidden Gauss-Markov models. So the improvements lies in the introduction of so-called continuity preference, so that whenever the models are such that the parameters of, let's say, the parameters of the models in the consecutive time steps are continuous. It shows much better performance than traditional time-varying Gauss-Markov models. So that that's yeah, and what is also important that such extension of the models allows learning from small data sets, which was shown and, let's say, validated on industrial use cases from industrial robotics, where we had the data representing power consumption of the machines. This was for the first part regarding data processing. Now, the second part regarding robotics and production is a use case focusing on multi-agent system in distributed production. So this is the setup of the use case that we provide here in testbed in CIIRC. And this is the architecture, or let's say the principle of the system. So you can see there are several agents that represent the machines. The machines can be robots, conveyors, or other types of machines in production or assembly processes. And then there are other types of agents, like directory service agents, which registers the agent capabilities of the other agents that are available, and then the product agent to negotiate the best product assembly conditions. This structure spans across several edge nodes in terms of the Brainy platform. It may be several nodes within one microdata center, or even across several microdata center, which supports the idea of distribution of the agents, so that they are not only locally in one factory, in one production hall, but can be distributed across much bigger space. This is an example of, or I would say, principle of the negotiation starting from the product agent, where the product searches for the agents that are available to provide the required capability, and based on that, then the plan is sent to the production or to the machine agents, and then after the negotiation, which is done by sending the planning request, getting the result, and then commit request, the production is the production can be started. So, as I said, this is the basic principle of the multi-agent communication and multi-agent negotiation, which is realized here. And these two parts were implemented now partially, but we've been on the track to final implementation. So the experimental setup is in the testbed for Industry 4.0 here in CIIRC. And this relates to the implementation of the multi-agent system, then to the implementation of the pattern discovery and behavior detection of the machines, which is based on the data acquisition from the robots that we have here. And last but not least, there is an IoT platform connected to provide the environment to store the fast time series data as well as, let's say, parameter data, which are not time demanding. And we're heading towards distributed production, where we are going to have an RC card composed of several parts, which will be composed at the production line, as I showed before, so that there will be some automatic warehouse, part delivery provided, performed by these mobile robots and also by this type of mobile robots. Then there will be some assembly performed and at different types of robots, and in the end, the assembled product will be available. And this is just to test the concept locally, but we are supposed to scale this up regarding individual processes. So, for example, if we take into account the tire assembly, which is executed here by a Delta robot with force feedback at the end effector. So the idea is to, after it is developed and tested here, I mean the process, then it can be transferred to other test bed in the consortium where we cooperate, which we cooperate with, namely the network of test bed within the RICAIP project. So in such a case, the same process will be available at other site, executed at other type of production cell with different parameters. And this will become an external agent that can enter the negotiations, but not locally within one production line, but across or among remote sites. So the same multi-agent principle will be used, but the agent will be considered as the whole production site, so that the negotiation principle will be the same, but at the higher level of the hierarchy. So based on this approach, we can include not only the production steps, but also the logistics steps into the planning and negotiation part, which allows to model logistics chain and also allows to include external disturbances at various phases of the production. So there is some, first of all, these are the capabilities, so that the agents must advertise or register their capabilities, and then there is a request to provide some operation, and the agent offers the cost, or for which cost? Auction, yeah. Mm-hmm. Okay, so I think that's all from my side.